All right, the directions for this one say to find the length and width of a rectangle that has the given perimeter and a maximum area. But instead of giving us a number for the perimeter, they give us P for perimeter. Now, if it's a rectangle, we know that the way you get the perimeter of a rectangle is add up, well, for anything, you add up all the sides. And for a rectangle, two of those sides you can call the length, two of those sides you can call the width, or you could have called them base and height, whatever. But you get 2L plus 2W or 2B plus 2H equals P. Okay? Now they tell us that they want and a maximum area. So the area, if I'm using L and W, is L times W, and that needs to be a maximum. All right, so we're good. Let's decide, we've got that. Let's decide on which variable we're going to work with and make our function a function of that one variable. Okay? So I decided, fairly much at random, that I was going to let W be the variable. All right, so if I had called this area function A of W equals LW. So this is my primary function, which means this then is my secondary function. The only thing it's really good for right now is to give me a way to solve for L to replace L. Yeah. No, I have to use this one as my primary because they gave us that. That's what we got to figure out. All right, but I could have, for instance, I could have made this A of L instead of A of W. Okay. All right, so take your perimeter function that they gave you, solve it for L, and then replace L with 1/2 P minus W. You with me? All right. Now, that function, let's simplify it as best we can, get us here. Then once we get the function written out, the rest of the problem should seem familiar. Now, that's real easy for me to say because it only took a few lines, but that's the hard part, isn't it? At this point, it ought to be the hard part. The rest of it, like I said, should be familiar because you're going to try to find critical numbers because that's where if we're going to maximize something, the maximum has to occur at a critical number. Then we're going to either do the first derivative test or the second derivative test, as you're probably starting to pick up on. I do the second derivative test whenever feasible because I can do it in my head most of the time. Okay? So once we get our function written in a fairly simple form, then it's good old-fashioned calculus. Take the derivative. So the derivative, remember what your variable is, it's W. The derivative of 1/2 PW, well, 1/2 P is the coefficient. So the derivative of that is 1/2 P minus, and then the derivative of W squared. Well, if it was X squared, it'd be 2X. So if it's W squared, it'd be 2W. Okay? So that's our first derivative. Find the critical numbers. So I set the first derivative equal to 0. Subtract 1/2 P from both sides. Divide by 2. And that's my critical number. Follow me? All right. Now, if this is my first derivative right here, it's real easy to get the second derivative, isn't it? Because 1/2 P is a constant. So the derivative of negative 2W is negative 2. All right, so that's good. That's good news, isn't it? Because we've got a critical number that comes from where the first derivative equals 0, and our second derivative is negative. Doesn't that mean relative maximum? Whenever the first derivative equals 0 and the second derivative is negative, that means relative maximum. And that's exactly what we have here. So the second derivative, when I evaluate it for 1/4 P, equals negative 2. Because the second derivative always equals negative 2. That means that the function evaluated for 1/4 P must be a relative maximum. So now I know what W is supposed to be. It's 1/4 P. I go back then and figure out what L is supposed to equal. So I'm using that, and I substitute 1/4 P in for W, gives me that. Simplify, gives me that. So the area is a maximum when the length equals 1/4 P and the width equals 1/4 P. Whenever you have a rectangle and you want to maximize its area, guess what shape you need to make? Square. Now, what the book will do to keep you from figuring that out after a time or two and then always knowing what the answer is going to be after that is they'll do weird things. Like they'll make you make a rectangle. They'll give you a building and they'll say make a rectangular pin there. Well, now that there's 3 sides instead of 4, you got to mess with it a little bit more. Or then they'll, and then they'll put a dog pin in the middle and you have to subtract that. They'll make it so it's not always a square. But if there's no other circumstances going on to maximize the area of a rectangle, make it a square. Uh-huh. Yep, sure is. All right. Does that help on number 10 a little bit? All right, what do you want to see next? All right, here's number 3. They said find 2 positive numbers that satisfy the given requirements. And for number 3, the sum is S and the product is a maximum. All right, so like the example we did yesterday, we need 2 positive numbers. So I called them X and Y. And so the sum of those 2 numbers is X plus Y. But then they want the product to be a maximum. So I call the product P. So the product, which is X times Y, is to be a maximum. And I went ahead and decided that X was going to be my variable. That's why I called that P of X. Okay? All right, so I've got the function I'm going to be dealing with right here. Then what's this one for? It gives us a way to solve for Y so we can replace it. Okay? That's what it does. So we do that. We take S equals X plus Y, and then we subtract, well, what did I do? I subtracted X from both sides, then I just flipped it so it looked like Y equals. So I subtracted X from both sides to get that. So that's what can replace Y. S minus X can replace Y. So P of X then is XY. All right, I'm on this line. P of X equals XY, but replace Y with S minus X. Now, that's the new stuff. So before we go on, questions on the new stuff? Yeah. Yes. Yeah. They don't tell us what the sum is, but they said it was S. So at that point, when they tell you something like that, S is S. It stays S. Okay? Anything else before we move on? All right. Now, from here, I've got my function, and I want to maximize it. So that means I want to find where its maximum value occurs, or what the maximum value is. I can't do that because they didn't give me really numbers. And in fact, the directions just say find 2 positive numbers that. So we're trying to find X and Y. All right? So I need to find where the maximum occurs, which means take the derivative. Before I take the derivative, I'm going to distribute that X and then take the derivative. So S is a constant, so the derivative of Sx is S, and then the derivative of x squared is 2x, like it's always been. That gets me here. You good? Okay. Now, to get a critical number, there is no denominator, so where does the first derivative equal 0? Well, set it equal to 0 here and solve. What I did was I subtracted s from both sides to get that, and then divide both sides by -2 to get that, because a negative divided by a negative is a positive. So s over 2 is my critical number. So if this function really can be maximized, x equals s over 2. But we've got to check to make sure that it really is a maximum, because remember, critical numbers can lead to a max or a min or to nothing. Okay? So there's nothing that says that just because we made up this function that it must be able to have a maximum value. So we got to test and see if it does. Well, the second derivative is easy. Using that as my first derivative, take the derivative. The derivative of s, since s is a constant, is 0. The derivative of negative 2x is negative 2. And that gets me the second derivative. All right, you guys with me now? Can you hear me now? What about now? Can you hear me now? All right. So we do the second derivative test, which is a piece of cake because the second derivative is always negative. So where the first derivative equals 0, s over 2, the second derivative is negative. I didn't even have to say that it equals negative 2. I just needed to state that it's negative. Okay? So since that happens, the first derivative equals 0, the second derivative is negative, that means that gives us a relative maximum. So whatever the value of P of s over 2 is, it's the maximum. Okay? Which means that x equaling s over 2 yields the maximum. Let's find out what y equals. Well, we go back to here where we had solved it for y. You plug in an s over 2 for x, and then s minus half of s is half of s. So it's s over 2. And then, lo and behold, the product P is a maximum when x equals s over 2 and y equals s over 2. That's too hard of a problem to be just number 3, isn't it? But it's not. It's s. But it's s. But yeah.
So it's just like the square, just the both added together, the product maximum is only 2.
So what are they going to do to prevent you from catching on to that and making every problem one-step problem from now on? They'll make you do things like make that a 2 and that a 3, and so then you got to actually figure it out. I don't know. It's kind of mean, isn't it? We're in the same section of problems, so we still have to find the two positive numbers that satisfy the given requirements. So let's let x and y be those two positive numbers. And for number 6, they say that the second number is the reciprocal of the first, and the sum is a minimum. Second number is the reciprocal of the first. So one of them is the reciprocal of the other one. So I decided to let y be the reciprocal of the other one. Okay? All right, what was supposed to be happening next? And the sum is a minimum. Well, the sum is x plus y. So s equals x plus y is a minimum. And we have to figure out what value of x, and then therefore what value of y makes that happen. So the sum would be x plus y, and I don't know, I guess I got lazy. I never wrote that out anywhere. The sum is going to be x plus y, so s of x will be x plus, and instead of y, put what y equals, which they told us it's the reciprocal of x, so it's 1 over x. So, you with me to that step? It's getting a little bit easier to see your way through them. All right, you know why that one was easier? They told us that instead of giving us a different equation and making us figuring it out ourselves. Okay? All right. Take the derivative. Derivative of x is 1. the derivative of 1 over x. Well, 1 over x is x to the negative 1. The derivative of x to the negative 1 is going to be negative x, subtract 1 from the exponent. So negative x to the negative 2, which is the same thing as that, which is the same thing as that. Why did I do all that to the derivative? Easier to get, no, because that way it's easier to get the critical numbers. Yeah, because now I can just look at it and tell what the critical number is. Can't be 0, because 0 is not a positive number. Can't be negative 1, because negative 1 is not a positive number. So the only critical number that fits our criteria is 1. Follow me? Okay, so x equals 1 is the only critical number in the domain. Now let's go ahead and get the second derivative. And let's see, where was I looking when I did the second derivative? Probably from here. All right, if I'm going to take the derivative of that, the derivative of 1 is 0, but then the derivative of negative x to the negative 2. Power rule it. Exponent times coefficient, that gives you a positive 2. X, subtract 1 from the exponent, which is the same thing as that. So that's how I get my second derivative down to here. So you follow me all the way down to the second derivative? Okay. Now, x equals 1 is our only critical number. So s double prime of 1, well, it's 2 over 1 cubed. It's 2. It's positive. So s double prime of 1 is positive. Where did 1 come from? It's a critical number where the first derivative equals 0. So whenever the second derivative is positive at a critical number where the first derivative equals 0, that is a relative minimum. So the sum is a minimum when x equals 1. And then go back up here. There's what y equals. Well, if x equals 1, what does y equal? 1. Number 22 says, determine the dimensions of a rectangular solid with a square base with a maximum volume if its surface area is 337.5 square centimeters. All right, so I was a little confused here, so I needed a picture. So I made a picture. And it doesn't really look like the bottom of that is a square, but it is, because I said so. So the bottom is x by x, and then I just made the height of it y. Have to call it something, right? Might as well call it y. So I've got that rectangular prism. And I've got to find the dimensions that give this a maximum volume. In other words, I've got 337.5 square centimeters of material to make the container. I want to make it in a shape that will allow me to put the most stuff in it that I can, which seems like a reasonable thing to want to do. Okay? You don't want to hold the least you can. That doesn't make sense. All right. So how do I go about this? Well, I know what volume is. I know that volume is length times width times height, or it's the area of the base times the height. Okay? I also know what surface area is, but it's a little more complicated to get. You know, I think, well, I don't need surface area. Don't write this down yet. I know that the volume is the area of the base, x times x is x squared, times the height. That's what I'm supposed to find the maximum of, so why don't I just do that? Or why don't I just do that? Got two variables in. Okay? I can't make that just a function of x because I've got a y there. Okay? So we're still doing what's called single variable calculus, not multivariable calculus. So we can't handle that. We're not equipped to. So we need to use surface area as our secondary equation so that we can solve for y and replace the y with whatever it is in terms of x. Okay? So, the surface area equals. All right, it doesn't have to be fancy. You find the area of each face and add them up. So you don't have to remember any formulas from geometry here. So down here on the bottom, what's the area of that if it's x by x? X squared. Well, isn't that the exact same as the area of the top? So 2x squared. All right? But then I've got faces like this. What's the area of that face? xy, right? X times y. Well, isn't that the same as this face? And the same as that face? And the same as that face? So there's 4 of them like that. So 4xy. So that's all 6 faces. Add the area up of all 6 faces, and that equals your surface area, which they so nicely told us is 337.5 square centimeters, because that's a very easy number to work with. That was sarcasm again. Y'all starting to miss out on that.
Since we're going to make it into a cube, why don't we take cube root?
But you don't yet know it's going to be a cube, because you haven't worked this problem yet. All right. But you don't know that. You have to write the theorem that proves that, or work the problem. Which would you rather do?
We're going to learn this theorem.
All right, so add to the homework I'm going to give you to write and prove the theorem that says that'll be a cube. Nope, that's not a theorem. That's a postulate. All right, now write down that V equals x squared y. It's a maximum, or at least it will be when we're through with it. Now go back up here to your surface area equation and solve it for y. So first step, subtract 2x squared from both sides. So I like my x squareds to be in front of my constants, so I wrote it as negative 2x squared plus 337.5. That's just personal preference. I like the good old, like you did with quadratics, descending order of exponents. I like that better. And what do we do next and last? Divide by 4x. So that's what y equals. And that's going to be easy to work with. Yes. See what I did there? Yeah. Math is fun. For me, at least. I'm having a ball. I don't know about you guys. All right, so now go back to your volume function and replace y with this nice little expression. And so v of x equals x squared times the quantity, negative 2x squared plus 337.5 divided by 4x. All right, and believe it or not, I can make this simple. Ish. Because, no, that wasn't sarcasm. I can do that, right? Divide the x in the bottom into the x squared outside, because that's an x squared in the top. It's an x squared over 1. So that leaves me with an x outside. What am I going to do with that x outside? I'm not going to throw it away. Instead, I'm going to and get that. That's the official name. And I can take the derivative like that. I can use the quotient rule, and it'll work out just fine. Or over 4 means divided by 4, doesn't it?
Yeah.
Divide by 4. So what's negative 2x cubed? divided by 4, negative 1/2 x cubed. And everybody knows that 337.5 divided by 4 is 80, is that a 4? 84.375 x. Oh, I thought you had to pass a test to get into this class that asked you what 337.5 divided by 4 is. Huh. All right, so we can take the derivative of that easily, as a matter of fact. What's the derivative of 1/2 negative 1/2 x cubed? Negative 3/2 x squared. And what's the derivative of 84.375x? 84.375. All right, so that's our first derivative. Let's find the critical numbers. So we set that equal to 0. Let's subtract 84.375 from both sides. Then let's divide both sides by negative 1/2, which gives you 56.25, positive now, negative divided by negative. And then take the square root of that. And I know you had to pass a test over the square root of 56.25. It's 7.5. As everybody double checks me on their calculator. Thanks for the confidence, guys. All right, that's our critical number. If this thing really can have a maximum volume, that's where it happens. So now we decide whether this thing really can have a maximum volume. Does it seem reasonable that it would? With a certain amount of material, does it seem reasonable there would be a maximum amount of stuff that would hold? Yeah. Would there be a minimum volume? No, you just keep flattening it out, and it holds less and less and less. I mean, 0, I guess, would be, but, you know. All right. Take the second derivative. So I'm taking the derivative of what I just circled in red. Well, the derivative of negative 3/2 x squared is negative 3x. The derivative of 84.375 is 0. So before we write it down, what's the second derivative test going to show us?
A minimum, or if it really is a maximum.
Yeah, it really is a maximum, because when I plug 3.7 or 7.5 into here, negative 3 times that will be negative. So since the critical number came from where the first derivative equals 0 and the second derivative is negative there, that yields a relative maximum. So let's say so. V double prime of 7.5 is negative, so V of 7.5 is a relative maximum. And what's the only thing left to do? Yeah, we got to find y, don't we? So y equals negative 2x squared plus 337.5 divided by 4x. So put 7.5 in for x. Wave your wand. See how I threw that in? And y equals 7.5. Which shockingly makes this shape a cube. So the volume is a maximum when x equals 7.5 and y equals 7.5. Number 34. Number 34, which is all the way over on page 225, says to rework exercise 33 for a cylindrical package. The cross section is circular. So I guess we better look and see what happened in number 33, huh? In number 33, a rectangular package to be sent by a postal service can have a maximum combined length and girth, which is the perimeter of a cross section. You learned a new word today, girth, of 108 inches. See figure. Find the dimensions of the package of maximum volume that can be sent. All right, so we're supposed to find the dimensions of the package of maximum volume, except we have a cylinder instead of a rectangular pyramid. All right, so I made a new picture, which you will now copy down on your paper, of a cylinder instead of a rectangular prism. Did I say pyramid a while ago?
Yeah.
Prism. Now, we got to use the same definition of girth. It's the perimeter of a cross section. Okay. Now, so if we combine the length and the girth of this cylinder, it equals 108. Okay? I'll call the whole thing girth. Just the perimeter of the cross section is supposed to be girth. Or is it the length plus? No, now I'm confusing myself.
So that when you say girth equals that, that's all.
Yeah. So the length of the cylinder is y. The girth of the cylinder, now circles don't have perimeters. We call them circumferences. Okay? So the circumference of the cross section, which is a circle, is going to be 2 pi r. So when you add the length plus the perimeter of the cross section, you get 108. So yeah, calling that girth is not right, but that equation is right. Okay. You more or less with me? More? All right. What do I need to re-explain? Just got to let it sink in a little bit. Okay. All right, now, that's not the equation that we want to maximize. Is it? No, what are we supposed to maximize? The volume. Okay? So thinking ahead a bit. Volume of a cylinder is the area of the base times the height. You don't have to write this down yet. What is the area of the base?
Pi squared.
What is the height? Okay? So that's going to be the equation we have to maximize. And it's got an x, or, well, an r and a y in it. So let's take this equation we already have written down, solve it for y. So we would subtract 2 pi r from both sides. So y equals negative 2 pi r plus 108. So the volume, which is pi r squared y, is a maximum. Now we want this volume to be a function of one variable only. So since I've solved it for y, that means I chose the other variable as the variable. So r is the variable. So v of r equals pi r squared. And then replace y with what we found out that it equals, which is negative 2 pi r plus 108. All right, distribute the pi r squared. So we get negative 2 pi squared r cubed plus 108 pi r squared. And that's not so bad to take the derivative of. Keep in mind that since pi is a constant, pi squared is a constant. So in this first expression here, r is the variable, okay? So when we do the power rule on that, exponent times coefficient, that'll be 3 times negative 2 pi squared to get negative 6 pi squared. R, subtract 1 from the exponent, plus, and then again on the second expression, keep in mind that r is the variable, pi is a constant. So when I power rule this, exponent times coefficient gives me 216 pi, r, subtract 1 from the exponent. So there's our derivative. I can factor. What can I factor out of that?
Pi r squared.
A pi r and also a negative 6. So negative 6 pi r times the quantity pi r minus 36. And then I went ahead and wrote equals 0 because isn't that what I'm wanting to do? Find the critical numbers. All right, for the factor that's outside the parentheses, the negative 6 pi r, what makes negative 6 pi r equal 0? 0. And if the radius is 0, does our cylinder exist? So 0 is not in the domain, is it? Pi r minus 36 equals 0. Add 36 to both sides, divide by pi, and that's the critical number that's going to work. Find the second derivative. So I'm going back up to this line. Again, the pi squared is a constant. So power rule it. Exponent times coefficient will give us negative 12 pi squared. R squared is now just an r. And then the derivative of 216 pi r is 216 pi. And I feel the need to factor this second derivative. This isn't quite as simple as just plug the number in. It's negative like we want it to be. So I'm factoring the second derivative because I can factor out a negative 12 pi, and that leaves me with a pi r minus 18 inside the parentheses. All right, so I didn't write this down, so I'll write it over here. I've got this. All right, so that's negative out in front. And then in the parentheses, when I replace r with 36 pi, pi's divide out, do I get a positive or a negative number inside the parentheses? Positive, and negative times positive, so I get a negative second derivative. Is that what I wanted? Yes. All right, so v double prime of 36 over pi is negative, so v of 36 over pi is a relative maximum. We know one of our variables then that leads to the relative maximum, r, is 36 over pi. We need to figure out what y needs to equal. So go back to our equation for y, which was way up here, and replace r with 36 over pi. And it works out kind of nice. Pi's divide out. Negative 2 times 36. What is that? 72. Negative 72 plus 108, 36. The volume is a maximum when r equals 36 over pi and y equals 36. Don't forget to conclude with a statement telling them exactly what they wanted to know. They wanted to know the dimensions that gave us that maximum volume.